Section: Introduction. In this section, we delve into how human cognitive processes have influenced the development of deep learning, particularly in the realm of neural networks. Initially, neural network designs were inspired by the brain's neuronal functions, using convolution kernels and hierarchical structures to imitate how humans acquire knowledge. More recently, transformers have introduced attention mechanisms to manage multiple information streams efficiently, enabling focused learning and achieving more profound sequential understanding. Thanks to the scalability of transformer architecture and pre-training methods, large language models, LLMs, and large multimodal models, LMMs, have demonstrated impressive reasoning capabilities akin to human performance, hinting at the potential of artificial general intelligence, AGI. Mathematical reasoning is crucial for these models, and various techniques like chain of thought, COT, program of thought, POT, and data augmentation are employed to guide LLMs in emulating human-like reasoning patterns. Visual mathematical reasoning poses a more complex challenge, requiring models to interpret visual information from images and solve problems based on textual descriptions. With the advancement of large multimodal models, researchers are increasingly utilizing them for visual mathematical problem solving, enhancing multimodal logical thinking abilities. To evaluate visual mathematical reasoning, previous studies have focused on challenging geometric problems, but newer benchmarks cover a broader range of disciplines. However, existing benchmarks often rely solely on end-to-end results for assessment, overlooking potential issues in the reasoning process of LMMs. To address this, we introduce WeMath, a benchmark comprising over 6.5K carefully selected visual math problems categorized into 5 layers of knowledge granularity across 67 concepts, ensuring comprehensive coverage. Real-world math problems typically involve multiple knowledge concepts, and their complexity correlates with the number of concepts involved. To assess a model's ability to solve such composite problems, we break down the process into 2 stages: solving individual subproblems corresponding to each knowledge concept and then integrating these concepts to arrive at the final answer. To evaluate the reasoning process accurately, we decompose composite problems into individual subproblems based on invoked knowledge concepts. Expert annotators break down these problems into one-step subproblems, guided by a 4-dimensional metric: insufficient knowledge, inadequate generalization, complete mastery, and rote memorization, to pinpoint gaps in LMM's problem-solving abilities. To address the insufficient knowledge issue, we propose a knowledge concept augmented (KCA) strategy, providing essential knowledge descriptions for LMM's reasoning. Our experimental results show that while some LMMs excel in visual mathematical reasoning, many struggle with multi-step problems, indicating a correlation between question difficulty and the number of knowledge concepts involved. Mastery of knowledge concepts is crucial for effective reasoning, yet many LMMs still face insufficient knowledge challenges, especially smaller-scale models. Our KCA strategy mitigates this issue, offering a pathway towards human-like reasoning. We highlight the importance of knowledge generalization and the prevalence of rote memorization in some models, underscoring the need for further advancements in mathematical reasoning capabilities. Section Summary. In this section, we explore how human cognitive processes have influenced the development of deep learning, particularly through the use of neural networks inspired by the brain's mechanisms. Transformers, utilizing attention mechanisms, have shown significant advancements in sequential learning, leading to the emergence of large language models, LLMs, and large multimodal models, LMMs, with strong reasoning abilities akin to human performance. To evaluate the reasoning capabilities of LMMs in visual mathematical tasks, we introduce WeMath, a benchmark comprising diverse math problems categorized based on knowledge concepts, aiming to address issues like insufficient knowledge and rote memorization in current LMMs. Section: WeMath. In this section, we present an overview of WeMath. Existing benchmarks often focus on results rather than the core aspects of solving math problems, leading to some unexpected evaluation outcomes. For instance, Math Vista suggests that LMMs perform better on university-level problems than on elementary-level ones. In contrast, WeMath is structured around textbook knowledge units, breaking down complex problems into smaller subproblems based on fundamental concepts. WeMath has three main features. 1. Hierarchical knowledge structure. WeMath follows the hierarchy of math concepts in textbooks, ensuring independence within the same level and logical connections across different levels. 2. Knowledge-based reasoning evaluation. WeMath investigates how LMMs solve problems by breaking them down into manageable subproblems based on fundamental concepts and using various measurement dimensions for detailed evaluations. 3. Knowledge concept augmentation. To enhance problem solving, we provide descriptions for 67 knowledge concepts from textbooks to support LMM's reasoning processes. WeMath focuses on fundamental math skills, categorizing problems into 5 types: plane figures, solid figures, transformations and movements of shapes, positions and directions, and measurements. These categories are further divided into 12 typical problems, which are then broken down into 67 knowledge concepts. We ensure each concept has 10 to 40 samples for balanced data. For data collection, we source 6.5K problems from reputable math websites, organize them based on our knowledge structure, and label each question with knowledge concepts. We categorize problems as 1-step, 2-step, or 3-step to understand how LMMs approach problem solving. An expert team verifies the consistency of questions, diagrams, answers, and alignment with the 67 knowledge concepts. In the problem definition, we introduce the evaluation dataset for LMMs, considering knowledge concepts and prerequisite conditions for each question. Inspired by Euclid's elements, we decompose problems into subproblems based on knowledge concepts to evaluate LMM's reasoning abilities. The decomposition process ensures logical coherence and helps identify issues in problem solving. Based on the decomposed problems, we assess LMM's performance by classifying responses into categories like insufficient knowledge, inadequate generalization, complete mastery, and rote memorization. We establish a reasoning hierarchy from insufficient knowledge to inadequate generalization to complete mastery, considering rote memorization as an unreasonable scenario. By enhancing generalization abilities, we aim to improve model performance. We propose a metric to judge the reliability of the reasoning process, emphasizing the importance of mastering fundamental concepts for solving complex problems effectively. Section Summary. In this section, we introduce WeMath, a benchmark that focuses on the essence of solving mathematical problems rather than just the results. WeMath is structured around textbook knowledge units, breaking down complex problems into subproblems based on fundamental knowledge concepts. By emphasizing hierarchical knowledge structures and knowledge-based reasoning evaluations, WeMath aims to enhance the reasoning processes of language model mathematics, LMMs, by providing essential knowledge support and meticulous evaluations. Section: Knowledge Concept Augmentation. In this section, we identified insufficient knowledge, IK, as a major challenge in mathematical reasoning. To address this, we had human experts create 67 knowledge concept cards crucial for LMM's reasoning process. These cards were developed by summarizing content from Euclid's Elements in textbooks, followed by extracting key knowledge hints through a series of questions related to specific concepts. After multiple reviews to ensure accuracy and usefulness, we finalized these knowledge cards. The figure in the paper illustrates typical knowledge concept cases and their descriptions. When faced with a problem Q_I and its corresponding knowledge concept K_I, LMMs use the relevant knowledge cards to find the answer A_I. More details about knowledge concept augmentation, KCA, can be found in the appendix. For our experiments, we created a test set called WeMath Test Mini, consisting of 1740 samples with different complexities: 1215 1-step, 362 step, and 165 3-step samples. We standardized all samples into a multiple-choice format for automated evaluation. We used regex to match the LMM's predictions with the ground truth answers and calculated their accuracy. Additionally, we employed a four-dimensional metric for assessment to prevent LMMs from deducing answers from the options by introducing an uncertain option. We evaluated the performance of foundation models in two categories on WeMath: closed-source LMMs, e.g., GPT-4o, GPT-4v, and open-source LMMs, e.g., LLAVA Next 110b, DeepSeek VL7b. The table in the paper presents the overall performance of different LMMs on problems of varying complexities and domains. We observed that the number of knowledge concepts in a question is related to its difficulty and impacts LMM's performance. Larger parameter scales in LLMs generally lead to better generalization abilities. In terms of math categories, GPT-4o performs well in calculations, while other LMMs struggle with precise visual measurements like angle measurement and unit conversion. Most LMMs excel in calculations but face challenges in conceptual understanding. LMMs show potential for parameter compression, with some models demonstrating competitive performance despite having smaller parameter scales. Optimizing visual representations is crucial for improving LMM's capabilities. Section Summary. In this section, we address the challenge of insufficient knowledge, IK, in mathematical reasoning by creating 67 knowledge concept cards with the help of human experts. These cards contain essential information derived from Euclid's Elements and textbooks, aiding LMMs in deducing answers to given problems. Through evaluations using the WeMath test miniset, we observe that the number of knowledge concepts in a question influences its difficulty and impacts the performance of LMMs, with larger parameter scales generally leading to better generalization abilities. Section: Knowledge-based reasoning analysis. In this section, we present the results of our analysis on knowledge-based reasoning. The table and figure provided illustrate the evaluation outcomes for knowledge-based reasoning under four different conditions: IK, IG, CM, ERM. We made several key observations. IK represents the primary vulnerability of large multimodal models, LMMs. Across all LMMs, there is a consistent issue of insufficient knowledge during the reasoning process, especially in models with smaller parameter scales like LLAVA 1.6 to 7b and DeepSeek VL 1.3b. Addressing this insufficient knowledge is crucial for advancing towards inadequate generalization, IG, and complete mastery, CM. The lack of knowledge in solving simple problems hampers progress in tackling more complex mathematical problems. GPT-4o's primary challenge has shifted from insufficient knowledge, IK, to inadequate generalization, IG, marking it as the first LMM to reach the knowledge generalization stage. While GPT-4o excels in addressing IK, it struggles with IG. Comparing the logical progression from IK to IG to CM, GPT-4o outperforms other models in converting IK into IG, indicating a shift towards addressing knowledge generalization challenges. The unreasonable ERM issue remains prevalent across most LMMs, with GPT-4o leading in addressing this problem. However, other models still struggle with ERM, particularly on the loose metric. Introducing the Knowledge Concept Augmented (KCA) strategy leads to consistent performance improvements in LMMs of varying parameter scales. While KCA effectively alleviates IK issues, it does not significantly enhance IG. This highlights the need for comprehensive improvements in knowledge generalization abilities for future exploration. Error analysis reveals that knowledge errors are the most common, emphasizing the importance of enhancing visual encoders' capabilities for fine-grained measurements in LMM's mathematical reasoning. In the realm of related work, various benchmarks have been developed to evaluate mathematical reasoning abilities in LLMs and LMMs across different domains, highlighting the need for comprehensive evaluation benchmarks to assess the strengths and weaknesses of these models accurately. Efforts are ongoing to address the gaps in evaluating multimodal perception and reasoning, aiming to enhance the overall performance and capabilities of LMMs.